See, there are let's n numbers of lateral forces might be coming to the structure, and it maybe depends on what kind of structure you are actually designing. Say an example, if you are designing some residential multi-story building, if it is subjected to some seismic activity or seismic active region, the earthquake forces or seismic forces are most common lateral forces. The actual earthquake force are actually having a nature of reversibility. Yeah, you all know that is not a unidirectional force. It is actually a wave. It is actually it's a random vibration force. If the nature of lateral force is kind of that, if it is a seismic, then the compression tension force may be reversible. When in the one moment, the one brace will be subjected to compression, the another moment, the same brace will going to subjected to tension force. So same member you have a compression and tension both. Opposite to that, if you are considering only unidirection wind design, so in the positive x direction, if you are having a load, then in the one direction only there is a connectivity or there is a effectiveness of the load transfer. For that, the member is subjected to compression on for a whole life. But that is case to case different. It has to be realized on an actual practical basis what kind of the nature of the lateral force and the actual structural usage, structural bracing, structural arrangement, everything is coming together. If brace are idealized as a tie brace only, see, if we have discussed in a previous slides that there is a tie brace only members. If it is even idealized as a tie brace only, that means it is idealized and modeled such that it can only take the tension forces. So in output, you might be having only tension forces. There will not be any compression force for that. So if brace are idealized as a tie brace only, then they will have only tension. In post-ending behavior, the forces in bracing system drastically changes, requires spatial attention and non-linear analysis treatment. Up to this 3 points, what has been written or what has been explained is up to the linear part of analysis. What actually, or the part of the analysis, what has been generally taught in our academics. But in a large earthquake scenario, and as we have discussed earlier, that in case of eccentrically braced systems, which are actually designed to take the large earthquake force only, and in that particular system, it has to do the nonlinear analysis. And what is the reason for that? That one, it is a post-yielding, that is a post-yield behavior. So when the material will be yielded to this highest limit, the forces in bracing system drastically changes because the capacity has now reached, and he will take one will take the force to the some limit and another is already post yielded. So it is yielded, his capacity already reached. Now it will stop to take the force. Hence the force system or the force path will drastically change. And for that requires a spatial attention and nonlinear analysis treatment. In some cases, the bracing may be required to take transfer loads along with axial loads, as we have discussed, like it's sulfate only. When we're considering sulfate, the sulfate is a kind of a transverse. So bracing is required to take. If the bracing size is considerably large, right? In the previous slide, we have seen one particular building is having the X brace from top to foundation. In that particular case of system, the bracing is having this considerable sulfate. For that case, you have to take transverse load in the action and in design also. So bracing may be required to take transfer loads along with the axial loads. Then the idealization of the same should be done accordingly during modeling. So that should be taken care during the modeling, right? So that's why the idealization is very important. And as we have discussed in our previous slide during the idealization and modeling. So that should be taken well in advance. Then and then you will get the structural actions according to that. See, if you are modeling the wrong way in a modeling is or idealization is not proper, your output from these computer programs will not be proper because the programs are not self-understood to the structural system. That should be done by our end. Right? That's why our skill is required. Coming to the next part is structural design of bracing member. So what is the structural design? So design is once you have actions from here in a numerical way, you are based on the that you are designing the systems. Depending upon the nature of the force, tension only, compression only, or both in reversible pattern. If it is a tension only, you have to design for tension only, right? So if required to take tension force only, if it is modeled such a way and idealized such a way, and it is required to, it will be going to provide in a practical way that it will take only tension. Like you are putting a rope, right, steel rope as a bracing, then obviously when it is will be subjected to some compression force, it will not take any force. But once anything you provide as a lateral force, which will actually producing the tension effect in that rope, it will be very much effectively, right? So that's a way when your model, you are idealized and you are actually practically provide the kind of brace which is tension only, then the design for tension carrying element should be done. If it is a Indian standard code, then you have to provide you have to do the design based on section 6 of the IS 800 2007, which is a limit state design code in an Indian scenario. If requires to take compression force only, in design for compression carrying element based on section 7 of the 800 2007, right? You have to do the design based on section 7. And if it is required to take both in reversible pattern, right? If you have if like the scenario we have discussed for the earthquake, design first for the compression. This is very important. This is very important. The single line what you have written here is not, you will not find anywhere in your academy, but it's always like in a practical way, it should be designed first for the compression and then check for the tension. Never do design first tension and then check for compression. You will not get a proper result. You have to do a more iteration, more and more iteration. So you have to design first for the compression and then check for the tension. You will get the most optimized section for in a very small trials or very few trials, right? Going to the connection design, as I discussed, this is very important in a practical way. When it's coming to the structural steel structures, the connections are very much important, right? So very important role in force transfer phenomena. If it fails, will break the path of the load transfer and hence should be critically checked and designed. Obviously, see, if you have designed sections or members, bracing members, beam columns very well with a very much safety, factor safety, but if the connection will fail, right, nothing, there is no meaning of providing any proper connection, proper members, because the connection is only the part which actually making the system to stand and to take the forces. Connection will break, right? There will not be any effectiveness. Even though the force is, even though the member is designed perfectly, it have a factor of safety over the requirement, then also it is not effective. Right? So steel structure, the connections is very much important. Based on nature of forces to be acted upon each element of connection, whether it is a weights or fasteners, gusset plate, it should be designed each and every part. If it is a weights, then weights should be designed properly. Fasteners like bolts and like to say rivets, then it should be designed properly. Gusset plate, even the connection members. So elements, connection elements like gusset plate, packing plate, right? Those are also to be designed properly. The guidelines provided in Section 10 of ISO 2007, along with minimum design actions and minimum strength requirements, should be followed. Here it is again not shown in our academia. This is actually requirement that any connection should take at least some minimum design actions or minimum strength, right? And that is been given in Section 10 of ISO 2007, and based on that, it should be designed. Let's quickly go to the one small case study, right? A comparative study between different bracing systems, right? So let's have some few systems and subjected to a same lateral force having geometrical parameters same, right? So here I will put up some pictorial way of 5 different systems, like 1, 2, 3, and 4. These 4 systems are concentrically braced frames, and as we've discussed, this is type 5, which is having a eccentrically braced frame, right? So this has been having the same geometry, right? The geometry is kept same, right? Even the members have kept same, and it is subjected to same lateral force at all 3 levels. And the deflection and maximum axial forces has been tabulated here for the comparison. You can see type 1 has a deflection 13.65 and member axial maximum axial forcing is one of them. Member is 148.65. Here type 2 8 mm deflection, 76.59 kilonewton force, Type 3, 9.83 mm deflection, 75 kilonewton force. Type 4, 10.45 mm deflection. The force is 75.56. Type 5 is having deflection 26.92. Look at 26.92. And the force is 75.06. So here you can see that apart from the first type, type force, type 1, all other four types having the maximum axial force is within the range of 10% only, right? So there is no much difference between the axial force here, right? But between 2, 3, 4, 5, the least deflection is 8 mm, as we have discussed in our past slide, that previous slide, that this X type bracing system is very much effective to control the deflection. So least deflection is coming here in this, right? There was a type 3 and type 4. So type 3 is having a second. So type 2 is a number one. I can say the force and the type 2 deflection control is very much here. Then type 3, then type 4, then type 1, and then type 5. Type 5 is eccentrically braced, which is having the force in the range compared to type 1. It's a least force to be resisted by brace. So it should be lighter in comparative. Here and here, type 1 and type 5, I will compare. The brace will be in here, the brace will be obviously, because it's 2, here is 1, it is going to be approximately half. You can see here is half of this force, approximately. Right? But still, the deflection here you can see is very much compared to this, almost double here, 13.65 here, 26.92. Right? Just quickly go through the deflection pattern and axial force for each type of the system. Right? See here, for the first type system, you can see the brown is actually the compression force, and blue diagram is showing the tension force. Here it is, green diagram is a deflected and a black one is actual, right? So you can see when one's first type and second type, you can see here both the bracing are taking the force. One is taking compression and second is tension, right? So compression, tension, compression, tension, compression, tension, right? One column is subjected to tension, one is subjected to compression. For this third type of system, here also both are subjected to tension, compression, both are tension, compression, right? Type 4, there is again tension, compression. Here you can see this. This is a gap, 1 meter gap between this. And there is also compression, tension going on. But I have not seen here the moment diagram. It might be having some, if you've been shown, you can see here the deflection, or sorry, moment here and shear between these two. And this is called the link. There's a very good picture of some industrial structure where both system has been provided. See here in yellow, you can see it is actually a concentrically braced system, right? X bracing. But here you can see this is a eccentrically braced system. It is not connecting. Here you can see there is no connection between the beam column and the brace. Actually, bracing is going through, but the connection is likewise, right? Going to the state of the art, what is the state of the art for this particular? Steel structures provide the speed and stringent quality control advantages in construction process compared to RCC, right? It's provide the speed and quality is also very good because the fabrication and the manufacture of the steel structure and the fabrication can be done in the shops, fabrication shops with the control environment. Quality control can be obtained. Versatile applications and modifications are also reason to choose the steel structure over concrete structure, right? You can have a versatile application, you can modify as you need, right? There is no much headache for the modification as well. Earthquake resistant design means design the bracing system to sustain the large lateral forces with maximum use of material strength and hence increasing the material utilization with cost optimization. You can do this way. Even you can design as a steel dampers in form of bracing to control the response of the structure. It's a large multi-story high-rise building. You can provide the steel dampers, or you can design steel structure. What is the advantage that when once it has been yielded, you can replace it. See, you can replace it. You can just simply remove that and you place the new brace, right? So that it is very much convenient compared to the RCC structure. So it is kind of a plug in your electric circuit. The plug, when the amperes or the current will be overloaded, The plug will diffuse first and will save the system. Same way, the steel dampers or the design of bracings can be done in the similar way. So it is a steel, so you can just remove that and put the new one, and your system is very much safe again. So it is very much preferred in the earthquake resistant design, and less in our country in India, but nowadays it is very much used in other countries, right? Wind resistant design of tall structures and bridges. Definitely, wind bracings are the special engineered to resist wind-induced stresses and control the behavior of the structures. Again, similar way, for the earthquake resistance, there can be used specially designed bracings for the wind resistant design. What could be the evolution in the field, which is a recent evolution? See, there is one name called buckling resistant brace frame system. This is called BRBF systems. Buckling resistant brace frame systems are specifically designed to take very much large earthquake forces as a compression member without going to buckle it. So what happening? If it is buckle, your material utilization will be less. Right? If it is not buckle, it will go to the yielding of the members, and for yielding, it will require the energy, and that energy is absorbed from the seismic activity. So whatever the seismic force is coming to the structure is passing that energy to that particular brace frame, BRBF, right? And the buckling resistant brace will absorb that energy by going to yielding and not buckling. So that is the evolution, and it is very much used in American countries. Even the EC American code is having a specific guideline to design for buckling resistant brace frame systems, and this it is the evolution in the field. So it has been widely accepted in American North America and that particular environment. Then you have a tensile grid structure. What is a tensile grid structure? It is a specifically designed structure where there is a combination of membranes and the steel members. So for that, the basic funda is only the bracings. The bracing is what is taking the lateral force. So tensegrity structure, the membrane will take the actions, which is gravity. Against that, the members, which are the bracing members, are taking the lateral forces or us to give the stability. Then ductile design of bracing. The bracings are that we have discussed. The design is such a way that ductile design is to take the specific forces. Retrofitting rehabilitation of existing building, which is very much advantageous of using the bracing. Nowadays, in a RCC structure or concrete structure, which are damaged to a some degree, which can be restored or retrofit or rehabilitated by providing the only steel brace, right? And that steel brace are specifically designed to take the earthquake forces. So retrofitting reliability of existing building is now doing using the bracing only. So those are the evolution in the field. Just buckling resistant bracing, I just giving the example. These are normal local behavior of brace. This is actually happening. If it is not buckling resistant brace, this is actually happening here. It will buckle out of plane, right? But when you provide buckling resistant bracing, it will not going to do that. Then ductile design, what we have designed, what we have just discussed, by avoiding local behavior of connection elements. Gusset plate yielding will be avoided by doing a proper ductile design. So the connection will be sufficient. Even though this member is designed, even this is buckling resistant brace, if this member will first buckle out, then also there is no meaning of providing these. So that's the ductile design. Coming to the career and job opportunity. So obviously, you can see the steel structures are widely used for wide varieties of industries like chemical, textile, thermal energy sectors, oil and gas, refineries, etc. Even the offshore structure constructions, pre-engineering building and industrial state structure designs, bridges, stadiums, towers, etc., etc. Right. So for all steel structures design, the bracings are required. The bracings are required for all of the above, and apart from these, it is widely used for retrofitting, re-strengthening, rehabilitation of work for several existing concrete and steel structures. So obviously, see, there is a wide applicability. There's not limitation. There is no limitation of use of bracing in a steel structure. Even braces are used for the retrofitting, as we have discussed in an existing concrete structure as well as. So there is a wide opportunity out there. to design or to make the career in steel structure design, because it's not limitation. And apart from that, very interesting to know that nowadays there is a scarcity of labor. So obviously with the scarcity of labor and need of the faster construction, day by day the requirement of faster construction is going on, the use of structural steel will increase and will be preferred more in construction of the residential and commercial building as well in the coming years, right? And it is being used right now in the mostly in the industrial structures, right, or special structures. But with the scarcity of labor coming to the faster construction requirements in the future, it will definitely going to replace residential and commercial building. It has started in a few major cities of India as well. You can see major buildings are going on in a steel in a Mumbai, in a Bangalore, in a Delhi, Noida, right? So this is there is a wide opportunity there, and because there is a little knowledge in the industry, in our Indian industry, practical design is very much less actually when compared to steel structure. It is limited. Few of them are very good to steel structures. So obviously compared to the RCC comparison to the RCC structure designers out there in the market, the steel structures are designers are very less. So for that you have a very good path, and you can take this path in steel structure. This is a career opportunity wide out there. You can go ahead with that. If you become a very good steel structure designer, you might be having an n number of opportunity out there in any kind of the industry. It will be used, right? So with this, thank you. I'm ending my presentation.